Good afternoon, everyone, and welcome to this fourth CPD webinar in our series covering the topics of how to model existing drainage systems and flood mapping with XPSWMM. There's still a few people logging in, so we'll just take a couple of minutes to introduce ourselves. My name is Peter Coombs, and today's webinar we are focusing on how to use best practice to forecast and respond to flooding. We'll show how to use XPSWMM to either mitigate and protect critical infrastructure items, or in very extreme circumstances, help on your emergency evacuation plans. And I'm really pleased to be able to introduce you to my two colleagues who will be actively participating with me today, and that's Samer Mohandes. Samer has recently finished his Masters in Civil Engineering at the University of Greenwich, after which he had done his undergraduate degree in Syria, and he's worked in Cairo as a construction site supervisor. So Samer's got site experience in the coalface there, as it were. And Ludmila Fedeva, Ludmila's a drainage engineer with 8 years of both design as well as modelling experience in the UK and overseas. And when I say overseas, that's really specifically in the Middle East region. Now, due to the numbers of people attending the webinar, we've had to mute you all, but please feel free to send us your questions. You'll see the little message box that's on your screen there. So feel free to send us a message, and we'll endeavour to answer them as we go along, or we'll provide a full written explanation at the very end of the webinar. And at the end, we'll upload an edited version of the video onto the website. We'll issue the QA sheets, and we'll send out a short survey monkey to you as well to solicit your feedback, which we much appreciate. So here's the agenda for the webinar. Should last about 30 to 40 minutes, and what we'll do is cover really the fourth and fifth steps in a systematic approach that we've been running through on this modelling series. Samer, Ludmila, and I will take it in turns to demonstrate these items live with XPSWMM software. And we'll be sharing the best practice, the best working practices on how we can forecast and respond to flooding, covering a range of options depending on the circumstances and those variety of circumstances to provide safety, but then balance this with the appropriate economic costs as well. There are times where in the process of gaining funding, etc., and working on these larger schemes, that the only feasible option is to provide evacuation plans, and in which case it's really a question of how much time do we have and what can we do in the short term. So we'll be showing you those items as well as we go through. So after my brief introduction, Samer is going to explore a variety of options in helping you to mitigate flooding through the creation of ideally additional space, such as floodplain channels, or we can provide storage facilities, and these could be either above the ground or below the ground. As we start entering in storage volumes under the ground, the costs increase exponentially, so it will depend on which is appropriate for your particular situation. After Samer, Ludmila will then show us how to protect the really vulnerable critical buildings, and that could be with sandbags, flood barriers, those kind of elements, and show you how we can model those within the software and assess their impacts by using time flow series indicators. So what we can do is we can look at the consequences of installing modeling flood barriers, but that may well have an effect on an adjacent building or a highway or a rail network or some kind of major infrastructure. After Ludmila's demonstration, she'll hand back to me, and then I'll show how we can set up and assess evacuation routes for those sort of critical infrastructure and critical buildings, illustrating how we can contribute towards emergency evacuation plans before I can draw on conclusions and introduce you to the next webinar in the series. So without further ado, I'd like to hand over to my colleague Samer Mohandes, and Samer will demonstrate how to mitigate for you.
Thank you, Peter. Good afternoon, ladies and gentlemen. It's good to see you all here again. As Peter mentioned earlier, we cannot hope to defend against all flood events, and that's why we need to be prepared and predict the changes and the consequences in order to build the resilience for our cities and be much more flexible and adaptable. And the bad news are, flooding will become much more worse in the future. We will discuss some structural and non-structural measures to respond to flooding, and I will start with the structural ones. As we cannot get the water to disappear, all what we can do is create space for the flooded water to flow. We can protect our structures by directing the flooding towards less important places or store this flooded water while we're having the extreme events. One of the ways to reduce the flooding is creating more space for the river to flow. Such a project was undertaken in the Netherlands. As you can see here, they were trying to create more space for the river to flow, which will reduce the possibility of flooding in extreme events. However, these kind of decisions have consequences. In this project, 50 homes and several businesses had to be relocated. So the concept of moving people and properties out of flooding areas in order to make room for flood water is socially quite a big step, and that's probably one of the biggest challenges in a project like that. Moving to XPSWMM, now we will see how can we model a process like that. We will see how we can create more space for the river in XPSWMM. So if I go to my model, here we have a river, and we want to create more space for the river to then in order that flooded water to flow in this new space. So I have two options to do that. The first one, through the multi-link, I can draw a multi-link, and then if I double-click on this multi-link or edit data, I can assign two cross-sections for the river, and then the water will be flowing in the two cross-sections or in two rivers. So this will be equivalent to two rivers. A better way to do that, and an easier way, is to modify the cross-section. So if I edit data for this river link, and I can easily modify the cross-section here. So if I add 2 points, and then to represent the new space, we can modify the cross-section. So this will represent the new space for the flooded water to flow. And then I can specify where is my new right bank and my left bank. If we say OK to that, now we have more space for the river. Another way to mitigate the flood is having a big storage areas. In some places, big storage areas should be considered to store the stormwater for some time while we're having the extreme event. And then we can feed it back slowly to our network. And this storage areas could be online storage or offline storage. Starting with the online storage, let's say that we have flooding here. If I check the long section and I hit play, we can see the flooding indicator, which shows us that we have flooding here. And if I check the result for this node, we can see that we have 2,635 cubic meter overflow. So now what we can do here, we can add a pond in this area. So we can convert this node to be a storage node. So if I double click on this node and then click on storage, and then add the dimensions of the pond. So let's say we have 1 meter pond and the surface area is 0.3 hectares. And if I say OK to that, we will notice that we have this triangle indicates that we have now a pond here. And if I analyze the model again, and we can check the long section. So we can see we still have flooding, but if we check the overflow volume, it went from 2,600 to 524, which is good, but we don't want flooding to happen at all. So what we can do in XPSWM, if you double click on this node, and if we click on storage, we can optimize this pond to contain all the flooded water. So I have two options, either to upsize the downstream pipe or upsize the basin. So here I will ask XPSWM to upsize the basin, then the water level doesn't go higher than 65. So if I say OK to that, and then if we analyze again after we solve the issue, now if you notice the model is trying to solve the problem and upsize the pond. At the end of the simulation, we will now check the overflow volume. So if I click on this storage again and check the overflow volume, well, we have 0 overflow volume. And if we check the long section as well, and we play, we will notice we don't have any flooding, and happy days. So if I close that, this way is called the online storage. And there's another way, which is called the offline storage, where we will put our pond in offline, off the network, and then the water will be flowing normally. But when the water level hits a certain level, it will go through this pipe, which is set in a high level, to be stored in this pond, and it will feed the network slowly back when the extreme event is gone. But you can ask why the water doesn't go that way in normal events. What we can do, we can double click, and from here we can put a non-return valve, which is here downhill only. So we will have the water only flowing that way, and we don't have any backwater. And this is the offline storage. If we go back to our slides again, we can see this is an example in Australia for big storage area. Some other countries, like Brazil, they're putting a big storage structure underneath football pitches. They have football pitches everywhere. And I think we have a similar one in Thatcham, close to Newbury. And in Sweden, they have designed a big storage area underneath the Roman amphitheater. So it's used around the world. Another way to mitigate the flooding is duplicating the thresholds of important buildings, such as subway stations. So we don't want to have flooding in the subway station as soon as the flooding hits the area. This is very important to protect the buildings and reduce the impact of flooding in some important buildings. So the use of raised thresholds makes really big difference in managing flood and building resilience in our buildings. So back to XPSWM, I will show you how we can model the threshold in XPSWM. We have a tool called the fill area. So if I right click on topography and add a new layer, and I can add a fill area, we can call it layer 2, for example. And let's say we want to put a threshold of 30 centimeters around this building. So we can model that. We can highlight the layer, and then using the polygon, we can draw a polygon around this building. And now we can set the new level after we raise the threshold, and let's say it's now 70.3. So when the water hits this building, we will have 30 centimeters, and then when the water depth is more than 30 centimeters, it will enter the building. And this is a very good way to represent the threshold. I did a similar one around this building, and when we analyzed, I'll show you here, you can see that the water is accumulating around the building, and the water depth is less than 30 centimeters, so it accumulates here, and it doesn't enter the building.
Samar, sorry to interrupt, it's Peter here, folks, but there's a question that's just come in from Samir, who's working in a city environment. And what he's saying is he's got a sort of situation where there's a threshold, and he's worried about flooding to a particular building, but that building's got a basement. So is there something that we can do in terms of modeling a basement under a building in a city environment, for example?
Yeah, thanks for this question. Very, very interesting one. Yes, we can model the basement storage. However, in this situation, we need to be careful about the grid size. We need to have small grids, very small grid cells. Because if your building have only 2 or 3 grid cells, you won't be able to model the basement and the basement. So in this situation, what we can do, we can draw a fill area around the building. And then we can use something called ridge break lines. So we can add this ridge break lines around this fill area. And here we will put the level for the fill area is the basement level. So let's say 69. This is the basement level. And then we put the ridge around the fill area. Here we will put the new elevation, which is 30 centimeters above, and to represent the raised threshold. So then when the water hits this ridge line, it will accumulate until the water level is more than 30, and then it will enter the building and it will be stored in the basement. So this is a good way to represent that. Some people represent this kind of process using the friction. So they increase the friction in this building using the land use layer. So they put a land use here, and they draw a polygon, and they increase manning. So when the water is flowing over the building, it will be delayed or retarded. So then in this way, we're representing some kind of storage for the water.
Yeah, exactly. We had another supplementary question from Jonathan on exactly that. No basement, but could I represent a building with a sort of high permeability or something like that? Is the question? Yeah.
Of course, we can. You can, using the land use, you can model whatever you want. You can even model green roofs. You can put the soil parameters, conductivity, porosity. But the most accurate way to model something like that will be flow constriction. And this is recommended when you have a fussy boss, and he's very, very accurate. So this is the accurate way. You can draw the polygon, full area, similar to what we've done. But then, instead of having a ridge around the instead of having a ridge break line around the building, we will use something called flow constriction. So we will draw a flow constriction around this building. And by doing that, we can now accurately model what's going on. So we can have 3 layers. And let's say the first layer represents the threshold. So we will say we have 100% blockage, and we can enter the loss coefficient. And after the threshold, we have the building from here to here. So, and let's say we have 1 door and 2 windows. So according to your openings, you will detect the percentage of blockage. And let's say it's 85. And then you enter the loss coefficient as well. And then after that, from the roof and higher than the roof, you have no blockage. So you have 0% blockage and 0 loss coefficient. So by doing that, you're accurately modeling the physical reality.
Great, thank you.
Yeah, you're welcome. Thanks for your question, folks. Very interesting ones. And now it's my pleasure to hand you over to Ludmila. Ludmila will show you how to model flood wall barriers and how to generate time flow series. Over to you, Ludmila.
Thank you, Summer. Now I will talk a little about mitigation actions. The most commonly used mitigation is a flood barrier. It can be permanent or temporary. Let's assume that we are desperate to protect a building. So I will bring back the background image to my model, and my area of interest is this big building here. It may be a school, museum, or a hospital. Either of these type of buildings are very important. So we want to set up a barrier around the building to make sure it's not flooded. Sounds good, isn't it? To do so, I click topography. If I go topography, add a new layer, elevation shape. So I would click add elevation shape layer, and once the elevation shape layer is there, I would just select a polyline and draw one. So in this particular model, I already have an elevation shape. I will just switch it on, and you can see the elevation shape. What I have done in here, I have two scenarios. So base scenario without elevation shape, and I have a second scenario which is called elevation shape scenario, which has the elevation shape. So we can compare. So if I double click on the elevation shape, a new windows come up, and there are a few options. We can either lower, raise, or change all elevations of the shape. In my particular case, I want to raise the elevation shape, and I want it to be raised to 72 meters of elevation. So this means I'm creating a permanent wall of 72 meters around the building. So it will be there at any minute of the time of our simulation. So the wall will always be there when we are simulating. So now, if we compare the results, if I go to base scenario and tick maximum water depth, we can see that the water is all around the building. And if I switch this scenario to elevation shape scenario, we can actually see that the water goes around the building. And now we can see as well what is happening around our wall. So if in the first instance, in a base scenario, we had only this big building flooded and a little bit of the building on right-hand side, and this area in here was almost not flooded at all. So now when we have a permanent wall installed, we can see what is the difference in spread of the water. The building on the right-hand side, which may be an electrical substation, is completely flooded, and the buildings on the left-hand side are flooded much more. So this means by saving a building, which may be, say, by saving a hospital in this town, we actually flooded an electrical substation, and it's not good as well. So before acting on any type of mitigation actions and building any flood walls, we really need to understand what impact the town will have upon this wall being up and standing. So all this can be modeled, and we can have different scenarios with different walls, and we can see how the water is spreading, and we can choose the most applicable option for us. But apart from using usual elevation shapes, we can create a dynamic shape, which means the shape will appear or disappear depending on conditions we set. For instance, if I want to model an inflatable wall, a pop-up wall, or a sandbag situation, so all I need to know where my temporary solution is going to be and what is going to trigger it. To do so, I need to click topography, add new layer, dynamic elevation shape. I add default layer 1, so I have a layer 1, then I select a polyline, and let's pretend I want my shape to come into here. So I double click, I have the shape. If I select it and double click on it, we have few more options which been added, and it's triggered by. So it means that this shape as well, it has options to either lower, raise, or change our elevation, but we can set the rules. We can set a start time, so when we wall, say if this is an inflammable wall, for instance, we want it to be inflated after a certain amount of time, then we can put in a time trigger, so start time trigger. If this is a pop-up or again inflammable wall, we can have a water level trigger, but then we need to add a trigger. So let me just close this down and add a trigger point. So if we go to topography, add new layer, trigger points, again layer 1, but we can say that we can name it as a river trigger or any other. So then we select a point, and I will press, and let me zoom in a little bit, and I will stick it here in a field. Now I will connect my dynamic elevation shape to my trigger point. So it is connected. I select it back and double click. So now you can see we have in here point 11. So I can stick water level at trigger point 11 at value, let's say 66. If we type in 66, and I want my wall to rise at a level of 68, so 2 meters high, and I want it to happen over 5 hours. So for instance, if we have a situation with a fluvial flooding, and we know that if the water reaches this point and the water level is 66, it gives us a huge indication that this development will be flooded. And we have maybe a fire brigade in a town who is more than welcome and happy to help us building some temporary barrier, maybe along this road. And we know that the mobilization time of a fire brigade with the sandbags is 5 hours from the point we call them till the point the 2-meter wall will be up. Right? So we can put all these parameters in here, press OK, run the model, and see how actually this type of mitigation helps or it doesn't help. So we can see what will happen. And we can model all different type of scenarios where we have an inflatable wall which will inflate over maybe half an hour, or we have a pop-in walls, or we can have just some manual barriers, and so on. As well, it can be triggered by water level difference. So if we can set 2 points and connect them all to the wall, and we can set a value of a water level difference. We can trigger it by depth or by difference in depth. So finally, I want to show you a tool called time series outputs. So it's good that we can model different mitigation actions and different flood walls, but what we usually want to know is how does the water levels or the volumes of water or the head or the velocity changes in some location. So if I just tick off the maximum water depth, right? So this building is maybe a museum where very expensive paintings are, and we don't want to flood it at any point of the time. So I want really to know what is happening along this line. So I do draw a line, and we can do it using time series output. So there is a line or a point. So I can either draw a line using the tools, or I can put a point using the tool. So I already have a line and I have a point in here. So now I want to know what actually is happening, how the water is crossing this line, and what is the hydrograph value. So just for better understanding, I will tick back the maximum water depth. And now I will click on time output series and show the flow graphs. So this is a flow graph for base scenario without the flood wall. We can see that the hydrograph is starting to build up after 1 hour, 30 minutes, and it goes up to 7 cubic meters per second. So the amount of water crossing this line reaches 7 cubic meters per second at a time of 5 hours, 4 to 5 hours. If I change the scenario where we have an elevation shape and I check the same flow graph, I can see that it actually goes up to 10 cubic meters per second, and it's almost like 5 to 6 hours a time. So we can see that the amount of water is much more after we put up the wall. we can check the same for the point. If I go back to the base scenario, and I do check show head and velocity graphs. So I have my head graph, and you can see that the head is constant, and this head is our ground level, our elevation level, right? And then the water starts to come in, and we have the increase of head, so the water depth is coming, and the point is here, right? So we can see actually what is happening in there along the time. I can show the velocity as well, so now we can see how the velocity is changing. So you can see at some point the velocity goes back to 0, but the head doesn't go back, so it means that the water is not coming in, but there is still some ponding at the area. If we go to the elevation shape scenario and we check for the same head and velocity graph, we can see it's constant because our point is inside the protected area. There is no water flowing through this point, so there is no difference in head or velocity. So all three lines are just lines. There is no change in it. That's it from me for today. Now it's my pleasure to hand you over to Peter, who will talk about evacuation routes.
Perfect. Thank you, Ludmila. And I'm just getting engrossed in this now. And if I go back to the original model that Sana was working with, what I'd like to do now is step away from the mitigation and the protection, because I hope you can see there's so many different ways that we can solve these particular issues given the right amount of time and the right amount of money. But in the interim, what about if we've just now been notified, look, we've got a big flooding situation, or we've erected some kind of a barrier and it's had an impact on somebody else. How do we warn people and how do we help them with their emergency evacuation plans, looking at the short-term solutions for them to protect the public at large? If I mark on the maximum depth of water, so if I just scroll down on the left-hand side here and show you what the maximum depth of water is, for this scenario that Ludmila's just shown us really, where we put in a barrier, but now there's a consequence. It's exactly what Samar was saying earlier on. For every action that we've installed, there's another consequence to somebody else. And there's a building under the water here to the left-hand side that we've got to take responsibility for. And we want to let the people know how much time they've got to evacuate this building and get to a safe place. Now, looking at the image right now, it would appear as though the logical thing would be for us to evacuate them to the west. Now, the river, the fluvial flooding, is coming from that west. So the flow in the river is coming from the west to the east. And we've been told by the local authority that this development here is going to be completely revamped and redeveloped, and they're going to build a protective barrier here in terms of site construction safety, so we cannot evacuate to the west. We're going to have to evacuate to the east, and what we need to do is evacuate up the highway that's hidden under the water here. So just taking a look at the profile, if I go from the building, and this is this building here that was under the water, if I just go up the road and just click a few points for you and just say, look, this is the route that we plan to take, and we're going to muster at this safe house, and this is going to be at a sports center or something like that. This is showing you the cross-section along which I've just clicked. So you can see that we're in a bit of a low spot from the building. We're going to go down into a basin, into a dip, and then we're going to walk up the road, up the hill to the muster station up here. Okay. How can we provide that kind of evacuation planning information? Well, looking on the screen, I'm going to move to the left-hand side. We have the option to identify evacuation routes. So under the water, what I've done, I've identified 3 routes up to the muster station, and I've covered the options of depth of the water, the flood water, the hazard rating of the water, and the velocity of the water. So how have I done that? If I right-click on evacuation routes, I'm going to add another layer 1. I'll just accept the default and say OK. And now, using the polyline, I can now identify from our building, which is here and under the water, okay, I can come up the highway. So this is the route we're going to walk. Now maybe this is a school, so we're going to walk the children and the teachers, etc., up to the junction, hang a right, and then we're going to muster in the car park here. Having established that line, I can select the line, and if I right-click on the line, I can then edit the data. And I could set this route up as a flood depth indicator. So if I insert just a row, click in the value, I could insert 0.1 meters depth of water. But I could add in additional layers. And basically, what I'm saying here to the program is, tell me how much time we have until the water reaches 100 millimeter depth along this line, anywhere along this line. I could add in another layer of 0.2, 0.3, 0.4, etc. And it will then tell me the time available until the water reaches those variety of depths. Okay, I'm just going to cancel on this right now, because in true Blue Peter fashion, if I switch that one off, here's one I've done earlier. It's exactly what I did in terms of the velocity. So the velocity along the line, if I maybe zoom in a little bit for you, is shown in the green line. Okay, so the velocity, I can mark on the actual figures if I come down to the reporting and show you the evacuation route cut-off times. So looking at the green line, if I zoom in a little bit further again on the plan view, you can see that we have just over 1 hour available to evacuate that building until the velocity reaches 1 meter per second. And you can change these parameters to suit your particular requirements. So that's showing us the velocity. If I just now click off the velocity and look at the hazard, so this is the velocity times the depth. I've set up a red line along the same route, and the red indicator is telling me that we have 2.52 hours, so just over 2.5 hours until the velocity reaches 0.29 meters squared per second. Now, typically, we're being swept off of our feet when we reach a threshold of 0.3 meters squared per second. So, in terms of that hazard, it would kind of make us feel quite reassured that we've got kind of 2.5 hours to evacuate people. Now, when we look at the depth, I've set the depth at 25 centimeters, 250 millimeters, and we've only got 0.74 of an hour, so we've got less than 45 minutes until the water reaches 25 centimeters depth along that route. So this is now telling me that that's the more critical scenario, if that indeed is the appropriate depth to have chosen. We've got 45 minutes to notify the people in the building, for them to muster, gather everybody, and then walk up the road. When I struck the line along the profile, we've got about 600 to 700 meters distance to walk. So that's going to take 5 or 10 minutes. So really what this is telling me is that we can tell people, you need to run emergency evacuation drills from that building and make sure that you can, from the moment the alarm is sounded, you have, say, 30 minutes available to then move from the building up to the muster point. That would be a part of our routine fire drills. Okay, so I hope you found that interesting, folks. Do feel free to sending any questions or emails to us, because we will answer them and send out some frequently asked questions and build upon that with the future webinars. But thanks for the participation, and thank you, Sama, and thank you, Ludmila, for once again showing us how versatile and how easy it is to set up a complete range of scenarios to enable us to either put in mitigation measures, put in barriers, or at the end of the day, if all else fails, we can at least give people some time warnings available to respond to those flooding issues that we're experiencing. So I hope you can all appreciate now how ideally we should be really making the space for the water in the first place. But if you have a retrospective situation, how we can create the optimum amount of storage as demonstrated by Samar in the first part of the presentation. If you have critical infrastructure, we can show you how you can model those barriers that Ludmila showed us, and we can look at the consequence of installing those barriers and use that time flow series indicator to show what the effects of that barrier will be on other areas of the catchment. And if all else fails, at least we can enable people to put together emergency evacuation plans. As I've just shown you, there's a full range of other inundation maps, etc., that I could show you as well. So if you need a particular demonstration to show you how to model a particular situation, then again, just drop us a line and we'll run a model for you and run a webinar to suit. Just to be aware that the training that we're running is on the 1st to the 4th of December. This is in Newbury here, so we look forward to welcoming those that have already booked. If you haven't booked, then please feel free to go to the website. If all the places are taken up, then we'll publish more dates for the new year. But that'll be the last time that we'll be actually running training this side of 2014. That seems incredible to say already. And the next webinar that we're planning to show you is on Wednesday, the 10th of December. And the information that we plan to run through on that, stepping away from flooding and surface water, we're going to show you how to model sanitary systems and combined sewers. And not just setting up the models, but also how we can model the transportation of pollution and contaminants through the networks. So we're going to start looking at the water quality aspects as well as the water kind of quantity aspects that we've been focused on the earlier part of the series. And what we'll do is we'll upload an edited version of this webinar. We've recorded the webinar for you, and we'll upload this onto the website for your colleagues that didn't have the chance to be able to sit in live. We'll produce a frequently asked question fact sheet and send that out to everybody, and post out a brief survey monkey to welcome all of your feedback as we're going through the series. So thank you all for your participation. I hope you enjoyed it as much as we did. I really apologize for my croaky voice, and I hope I've got a better voice for the next webinar in December, and we wish you all very well.
Yeah,
Thank you.
Thank you.
Bye-bye.